Hi students, welcome back to our online class. Today I am going to discuss about the continuation of magnetic effect of electric current chapter. In this chapter, the topic going to be discussed is Loren force. The topic is Loren force from the chapter magnetic effect of electric current. Loren force. Right. Before going to this, suppose let us consider an object which is placed on the surface of the earth. Which is placed on the surface of the earth. Right. So this is an object which is placed on the surface of the earth. Right. Due to gravity, this object experiences a force. It's called gravitational force. Gravitational force. Right? If any object which is placed on the surface of the earth due to gravity or under the influence of gravity, the object experiences a force is called gravitational force. Gravitational force. Right? Suppose the same object is dropped from a certain height near the surface of the earth. The same object is dropped from a certain height near the surface of the earth. Right. Once again, this object experiences gravitational force under the influence of gravity. Under the influence of gravity. So, from these two examples, it is clear that if an object is placed on the surface of the earth or which is dropped from the surface of the earth, in both cases, the object experiences gravitational force. Gravitational force. Whether the object is at rest or if it is moving due to gravity, the object experiences gravitational force. Gravitational force. Right. Okay. On the other hand, let us consider an electric charge. Right. You know that the electric charge is generally represented by the letter Q. Either small q or capital Q, right? Let us consider an electric charge, right? Which is placed in the uniform magnetic field. This charge is placed in the uniform magnetic field whose intensity is B, right? So Q be the electric charge, B be the magnetic field which is kept rest inside the magnetic field or which is placed inside the magnetic field, right? If the electric charge is placed inside the magnetic field, the electric charge does not experience any force due to this magnetic field. The electric charge never experiences force due to the magnetic field if the electric charge is kept rest inside it. Right. Suppose the same electric charge moves inside the magnetic field, it experiences a force. Right. If the electric charge is placed inside the magnetic field, that is which is at rest inside the magnetic field, it does not experience any force. It does not experience any force. However, if the electric charge moves inside the magnetic field, it experiences a force. It experiences a force. That force is called magnetic force. Magnetic force. Right? So, the electric charge experiences magnetic force only if the electric charge moves inside the magnetic field. If the electric charge is at rest inside the magnetic field, it never experiences any force. It never experiences magnetic force. But in the previous case, if the object is at rest on the surface of the earth or if it is moving towards the earth, in both cases or both situations, the object experiences gravitational force. But in this case, the electric charge never experiences magnetic force if it is rest inside the magnetic field. But if it is moves inside the magnetic field, it experiences magnetic force. It experiences magnetic force. Right. The magnetic force experienced by the particle when it is moves inside the magnetic field is given by the formula that is in vector form. F vector is equal to Q of V vector plus B vector. F vector equal to Q of V vector plus B vector. What is Q? The magnitude of the charge of the particle, given particle, right? And what is V? The velocity of the particle with which it is moves inside the magnetic field. And B, magnetic induction or magnetic field intensity, or simply we can say magnetic field, right? Are you clear? If any electric charge is moving inside the magnetic field, it experiences a magnetic force. The magnetic force experienced by the particle is given by F vector is equal to Q of V vector cross B vector. Q of V vector cross B vector. Q, the magnitude of the charge, V, the velocity of the charged particle, and B, magnetic field in which the charged particle moves. Magnetic field in which the charged particle moves, right? Suppose instead of a magnetic field, there is an electric field. Suppose there is a uniform electric field. Uniform electric field, right? Now the charge is placed inside the magnetic field. Okay, the charge is kept stationary in the electric field, right? So here, even if the electric charge is stationary in the electric field, it experiences a force. It experiences a force. That force is called electric force. Electric force, right? And electric force is given by F vector is equal to Q into E vector. F vector is equal to Q into E vector. Here, the charge is placed inside the magnetic field. It does not experience magnetic force. But if the same electric charge is placed inside the electric field or keeping stationary in the electric field, it experiences a force is called electric force. It is given by F vector is equal to Q into E vector. Q into E vector, right? Suppose if the electric charge is moves inside the electric field. The electric charge moves inside the electric field. Now also it experiences electric force. It is given by the same formula, that is F vector is equal to Q into E vector. Q into E vector. In the case of magnetic field, if the electric charge is stationary, the charged particle does not experience a force. But if it is moves inside the magnetic field, it experiences a force. The name of the force, a magnetic force, it is given by F vector is equal to Q of V vector cross B vector, right? In the case of electric field, whether the charge is stationary or if it is moving, it experiences electric force. It experiences electric force. It is given by the formula F vector is equal to Q into E vector. F vector is equal to Q into E vector, right? Suppose there is both electric field and magnetic field. Both electric field and magnetic field. So in this region, electric field and magnetic field also exist, right? Now this charge is moves inside this combination of electric field and magnetic field. Okay, the electric charge is allowed to move in the combination of electric field and magnetic field, right? So here, due to this electric field, the charged particle experience electric force. Due to this magnetic field, the charged particle experience magnetic force, right? Under the influence of both electric field and the magnetic field, the charged particle experience a force. Okay, the force experienced by the charged particle due to the electric field is electric force. Because in the case of electric field, if the charge is stationary or the charged particle moves inside the electric field, it experiences electric force. But in the magnetic field, if the charged particle is stationary, it does not experience magnetic force. But if it is moves, it experiences a magnetic force. Here, the charged particle is moves in the combination of electric field and magnetic field. So, the charged particle is affected by both the electric field and magnetic field. It means the charged particle experiences forces due to both the electric field and magnetic field. So, the total force or net force experienced by the charged particle due to this electric field and magnetic field is given by F vector is equal to Q into E vector plus Q of V vector cross B vector, right? What is Q into E vector? So this is electric force experienced by the charged particle when it is moves in the electric field E, right? What is the Q of V vector cross B vector? This is a magnetic force experienced by the charged particle whose magnitude is a q, which is moving with a velocity of v in the magnetic field of induction B, right? Here in this region, both the electric field and the magnetic fields are exist. So the total force or net force experienced by this charged particle due to this electric field and the magnetic field is given by F vector is equal to q into E vector plus q of V vector plus B vector, right? Here in this equation, q is common, so take outside. So q of E vector plus of V vector cross B vector. This force is called Loren force. The force experienced by the charged particle under the influence of electric field and magnetic field is known as Loren force. The Loren force is given by F vector is equal to q of E vector plus of V vector cross B vector. Q of E vector plus of V vector cross B vector. So this is Loren force, this is electric force, this is magnetic force. Magnetic force is also called magnetic Loren force. Magnetic force is also called magnetic Loren force. Right, next topic, force on a moving charge in a magnetic field. Right, already I told, if any electric charge moves inside the magnetic field, it experiences a magnetic force. It experiences a magnetic force. Right, let the q be the charge which is moving with a velocity of v, okay, in the uniform magnetic field of induction B. In the uniform magnetic field of induction B. Right, so due to this magnetic field, this charged particle experiences magnetic force. Right, it is given by F vector is equal to q of V vector plus B vector, right? So if the charged particle is moving with a velocity of v in the uniform magnetic field, due to this magnetic field, the particle experiences a force which is given by F vector is equal to q of V vector cross B vector. F vector is equal to q of V vector cross B vector. This force is called magnetic force, or is also called magnetic Loren force. Magnetic Loren force because the special features of magnetic Loren force is formulated by H.A. Lorentz. A scientist, H.A. Lorentz, was the first one formulated the special features of magnetic force. Special features of magnetic force. So that is why the magnetic force is also called magnetic Loren force. Magnetic Loren force. So Lorentz formulated the special features of magnetic magnetic force. Magnetic force. Right. So what are the special features? So first one, if the charge Q is at rest, the magnetic force experienced by the charged particle is 0. Right? So first special feature, if the electric charge is at rest, that is stationary in the magnetic field, at rest in the magnetic field, the magnetic force acting on the charged particle is 0. The magnetic force acting on the charged particle is 0. Right? And the second case, if the charged particle, that is Q, is moving either parallel or anti-parallel to the magnetic field, the magnetic force acting on the charged particle once again 0. Right? So if the charged particle is at rest, or the charged particle even moving inside the magnetic field, okay, in which direction? Either along the direction of a magnetic field or opposite to the direction of a magnetic field, okay, the magnetic force experienced by the charged particle is 0. Right? In both cases, or in two situations, the magnetic force acting on the charged particle is 0. First one, if the charged particle is stationary in the magnetic field, Fm value is 0. The magnetic force is denoted by the letter F suffix m. So magnetic force is 0 if the charge is at rest in the magnetic field. Right? And second, suppose the magnetic field is acting in this direction. Magnetic field is acting along the positive x-axis direction. The charged particle also moving along this direction means the magnetic force acting on the charged particle is 0. The magnetic Lorentz force or magnetic force acting on the charged particle is 0 if the charged particle even moving, but its direction is along the direction of a magnetic field, right? Suppose if the charged particle is moving like this, okay, that is the direction of motion of the charged particle is opposite to the direction of a magnetic field, which is called anti-parallel to the magnetic field. Anti-parallel to the magnetic field. In this case also, the magnetic Lorentz force or magnetic force acting on the charged particle is 0, right? Okay, so in two cases or two situations, the magnetic force acting on the charged particle is 0, right? Are you clear? Right. Next, already I told the magnetic force experienced by the charged particle in the uniform magnetic field is given by the relation F vector is equal to Q of V vector cross B vector. So this is vector form of magnetic force. Vector form of magnetic force. The magnitude form of magnetic force. The magnitude form of magnetic force is given by F is equal to QVB sin theta. Vector form of a magnetic force or magnetic Lorentz force, F vector is equal to Q of V vector cross B vector. But the magnitude form of Lorentz force or magnetic Lorentz force is given by F equal to QVB into sin theta. What is theta? Theta be the angle between velocity and the magnetic field. The angle between the velocity of the particle and the magnetic field. So this is a magnitude form, right? Now we go for the special features of a magnetic Lorentz force. Already I discussed two special features, right? And third one, the magnetic force experienced by the charged particle is directly proportional to magnetic field. The magnetic force experienced by the charged particle is directly proportional to the magnetic field. Directly proportional to the magnetic field. It means if the strength of the magnetic field is more, the charged particle experience a maximum Lorentz force or maximum magnetic force. Maximum magnetic force. If the magnetic field increases, automatically the magnetic force experienced by the charged particle also increases. If the magnetic field is decreases, the force value also decreases. So that is why the magnetic force is directly proportional to magnetic field. Magnetic force is directly proportional to magnetic field, right? And next, fourth one, the magnetic force experienced by the charged particle is directly proportional to the velocity of the charged particle. Directly proportional to velocity of the charged particle. For a given magnetic field of induction, if the charged particle is moving with greater velocity, the magnetic force acting on the charged particle is greater. If the particle moving with less velocity, the force acting on the charged particle is lesser. So, if the velocity is more, the force on the charged particle more. If the velocity is less, the force acting on the charged particle also less. So, the magnetic Lorentz force or magnetic force is directly proportional to velocity of the charged particle. Velocity of the charged particle. Right, next. The magnetic Lorentz force is directly proportional to the magnitude of the charge. The Lorentz force or magnetic Lorentz force acting on the charged particle is directly proportional to the magnitude of the charge. Right? Suppose for example, if the charge value is 10 coulomb. Suppose the magnetic force experienced by the charged particle is F1 for a given magnetic field for a given velocity. The velocity V and magnetic field is B. The charge value is for example 10 coulomb, which is moves inside the magnetic field. Suppose the force acting on the charged particle is taken as F1, right? If the magnitude of the charge is 100 coulomb and moving with the same velocity, that is V, in the same magnetic field B. Now the force acting on the charged particle is differ from F1. Now it is taken as F2. So comparing F1 and F2 is greater than F1. Right? Why? Because if the magnitude of the given charge is more for a given, moving with a given velocity and a given magnetic induction, the force acting on the charged particle also more. If the magnitude of the charge is less and the magnetic force also less. So Fm vector is directly proportional to Q. So Lorentz force magnetic force is directly proportional to magnetic induction, and magnetic force is directly proportional to velocity of the charged particle, and magnetic force is directly proportional to the magnitude of charge. Right. And next, right, we know that force is a vector quantity. What is vector quantity? If any quantity that has both the magnitude and the direction, then it is called a vector quantity. One of the best example for vector quantity is force, right? So here, by using this equation f suffix m is equal to q v b sin theta, we can calculate what is the magnitude of magnetic force. Right? Then what is the direction of magnetic force? Right? The direction of a magnetic force is perpendicular to v vector and b vector. The direction of Fm vector is perpendicular to v vector and b vector. Right? Suppose a charged particle is moving in this direction. Suppose a charged particle moving with a velocity in this direction, and magnetic field is acting in this direction. Right? The direction of a magnetic force experienced by the charged particle becomes this type, that is this direction. Suppose if the particle is moving in this direction and magnetic field is acting here, okay, the direction of a magnetic force. Suppose the magnetic field acts in this direction and velocity direction is in this, means the direction of a magnetic force is downward. So by using Fleming's left-hand rule, we can find out what is the, or we can determine the direction of a magnetic force. So direction of a magnetic force can be determined by using Fleming's left-hand rule. Okay, later we will discuss about that. Right. So here, if the charge is at rest in the magnetic field, magnetic force acting on the charged particle is 0. If the charge is moving either parallel or anti-parallel to the magnetic field, magnetic force is 0. And magnetic force is directly proportional to magnetic field, or the magnitude of magnetic force is directly proportional to the magnetic field. And magnetic force is directly proportional to velocity of the charged particle, or magnitude of a magnetic force is directly proportional to velocity of the charged particle. And last, the magnetic force is directly proportional to charge. And next one, the direction of magnetic force is perpendicular to the plane containing v vector and b vector. Right? And next one, suppose if the given charge is positive, and suppose it is moving with a velocity of v in this direction, and a magnetic field is acting perpendicular to the plane of the board and inverse. According to Fleming's left-hand rule, here stretch the first 3 fingers of the left hand, they are mutually perpendicular to each other. Right? Here the forefinger represents the direction of magnetic field. And the middle finger represents the direction of current. Right? And what is the direction of current? By convention, the direction of current is taken as along the direction of movement of positive charges. If the positive charge is moving in this direction, means the electric current direction also the same direction. Right? If it is a negatively charged, the direction of a current is taken as opposite to the direction of a movement of a negatively charge. Right? Here the negative charge movement is in this direction, so current direction also the same direction. Right? Here the magnetic field is acting perpendicular to the plane of the board and inverse. Right? Okay, by using Fleming's left-hand rule, the magnetic force experienced by this charged particle, that is positively charged particle, can be determined. Right? Apply this. Forefinger represents the direction of a magnetic field, right, acting perpendicular to the plane of the board and inverse. And middle finger represents the direction of current. What is the direction of current? The direction of movement of a positive charge is nothing but the direction of a flow of current. Here positive charge is moving in this direction, so velocity direction also the same, right? And here the thumb finger represents the direction of a force. So the magnetic force direction is upward. right? Okay, in this example, it is clear that if the magnetic field is acting perpendicular to the plane of the board and inverse, and the positively charged particle is moving along positive x-axis direction, the direction of force experienced by the charged particle is upward by applying Fleming's left-hand rule. Right? Suppose if it is negatively charged, the magnetic field direction is still perpendicular to the plane of the board and inverse, and which is moving along the same positive x-axis direction. Right? What is the direction of current? The direction of current is opposite to the direction of movement of negatively charged, that is electron. Okay, opposite to the direction of movement of electron. Right? So once again apply Fleming's left-hand rule. Forefinger represents the direction of magnetic field. But what about current direction? Current direction is opposite to the direction of movement of negatively charged. So taking like this. Right. Here current direction is this. And what is the direction of force? The direction of force is downwards. The direction of force is downward. So if the charge is positive and magnetic field is acting perpendicular to the plane of the board and inverse, and the direction of movement of a positively charged particle is along positive x-axis direction, means the magnetic Loren force is acting upwards. If it is a negatively charged, the magnetic field is perpendicular and inverse, and the direction of movement of charged particle is the same positive x-axis direction, but the direction of force is downwards. Direction of force is downward. So from this it is clear that the direction of magnetic force acting on the negatively charged is opposite to the direction of the magnetic force acting on the positively charged particle. The direction of force acting on the negatively charged particle is opposite to the direction of the magnetic force acting on the positively charged particle, but other condition does not change. Other condition means the magnetic field and velocity remains constant. Only the charge is first considered positive and later negative. Okay, only the sign of the charges alone changes, but keeping magnetic field and velocity is constant. Okay, constant. So the direction of a positively charged, the direction of Loren force or magnetic force experienced by the charged particle is upward, and the direction of a force acting on the negatively charged particle is downward. So force direction is opposite if the sign of the charge changes. So these are the special features of magnetic force formulated by Lorentz. So what are the special features? If the charge is at rest, the force on the charged particle is 0. First one. Second, if the charge is moving either parallel or anti-parallel to the magnetic field, the magnetic force on the charged particle is 0. Third, the magnetic force is directly proportional to the magnetic field. That is, the magnetic field increases, magnetic force also increases. And next, the magnetic force is directly proportional to the velocity of the charged particle. If the particle enter the magnetic field with greater velocity, the force on the charged particle is greater. Less velocity, force is lesser. Right. And next, the magnetic force is directly proportional to magnitude of charge. If the charge magnitude is greater, the force acting on the charged particle also greater. If the charge magnitude is lesser, the force also lesser. And next, the direction of Loren force acting on the charged particle is perpendicular to the plane containing V vector and B vector. That is, Fm vector is cross product of V vector and B vector. The magnetic force is the cross product of V vector and B vector. It means the direction of a magnetic force is perpendicular to both V vector and B vector. Then last one, the direction of magnetic force acting on the negatively charged particle is just opposite to the direction of the magnetic force acting on the positively charged particle. So these are the special features of magnetic Loren force formulated by Lorentz. Already I told, whenever an electric charge moves inside the magnetic field, that is other than the direction of a magnetic field or opposite to the direction of a magnetic field, it experiences magnetic force or magnetic Loren force. It is given by the formula F suffix m is equal to Q VP sin theta. Suppose what is theta? Angle between the velocity of the charged particle and the magnetic field. Suppose the charged particle is moving with a velocity v perpendicular to the direction of magnetic field. Perpendicular to the direction of magnetic field. In that case, theta value is 90 degree. Theta value is 90 degree. So substitute theta equal to 90 degree here. Then sin 90 becomes 1. Sin 90 1. Then this equation becomes F suffix m is equal to Q V into B. Right. Or this equation can also be written as B is equal to F suffix m divided by QV. B is equal to F suffix m divided by Q into V. Suppose if the magnitude of the given charge is 1 coulomb. Generally 1 coulomb is, or can be say, unit charge. A charge whose magnitude is 1 coulomb means then it is called unit charge. Unit charge. Suppose here the charge is a unit charge, and which is moving with a velocity of 1 meter second power minus 1. So this velocity is called unit velocity. Unit velocity. Under the influence of magnetic field, suppose the charged particle experience a magnetic force, suppose whose value or magnitude is 1 Newton, that is unit force. Unit force. If unit charge is moves with the unit velocity, it experiences unit force means then the strength of the magnetic field becomes 1 Tesla. The strength of the magnetic field becomes 1 Tesla. So 1 Tesla is defined as if a unit charge is moving with a unit velocity perpendicular to this magnetic field, and experiences unit force is known as 1 Tesla. So this is a definition of 1 Tesla. Once again I repeat, okay, the strength of the magnetic field is said to be 1 Tesla if a unit charge is moving with the unit velocity in the magnetic field, perpendicular to this magnetic field, and experiences unit force. So this is the definition of 1 Tesla. Right, next topic, motion of a charged particle in a uniform magnetic field. Right. Suppose let us consider a uniform magnetic field. In this region, there is a uniform magnetic field which is acting in this region. Suppose that magnetic field is acting perpendicular to the plane of the board and inverse. Right? Here, this crosses indicates the direction of a magnetic field, okay, which is acting perpendicular to this board, perpendicular to the plane of the board, and this magnetic field strength is denoted by B. This magnetic field strength is denoted by B, right? And there is a positively charged particle, that is a Q, and which is moving with a velocity of V vector. In the uniform magnetic field of induction, B vector, right? So if the charged particle, suppose moving perpendicular to this magnetic field with a velocity of V, so the particle experiences magnetic force. It is given by F vector is equal to Q of V vector cross B vector. The direction of a magnetic force is perpendicular to V vector and B vector. The direction of magnetic force is perpendicular to both V vector and B vector. By using Fleming's left-hand rule, the direction of force experienced by this positively charged particle is acting like this. So this is the direction of a magnetic force. The vector form of a magnetic force, Fm vector is equal to Q of V vector cross B vector. From this equation, it is clear that the direction of a magnetic force is perpendicular to the plane containing V vector and B vector. And the magnitude of magnetic force experienced by this charged particle is given by F suffix m is equal to QVB sin theta. Here the charged particle is moving perpendicular to this magnetic field, so theta value is 90 degree. Therefore sin 91, then Fm is equal to QVB. So this is maximum magnetic force experienced by the charged particle. When the charged particle experiences maximum force, if it is moves perpendicular to the magnetic field. If the charged particle is moves perpendicular to the magnetic field, it experiences maximum magnetic Loren force. It is given by F suffix m is equal to QVB. F suffix m is equal to QVB. Right. So here, this magnetic force acts as a centripetal force. The magnetic force or maximum magnetic force experienced by the charged particle acts as a centripetal force. Centripetal force. Already you are familiar about that because you have to study it in the lower classes. What is meant by centripetal force, right? So this magnetic force acts as a centripetal force. Centripetal force, right? So the charged particle is moving along the circular path, right? If the charged particle is moving with a velocity of v in the uniform magnetic field of induction, okay, whose direction is perpendicular to this magnetic field, it experiences maximum magnetic force. This maximum magnetic force acts as a centripetal force, so that the charged particle is moving along the circular path. Moving along the circular path, right? Magnetic force QVB, and the centripetal force is given by the formula mv square divided by r. mv square divided by r. M, the mass of the given charged particle. Mass of the particle, mass of the charged particle, mass of the charged particle, right? And v, the velocity of the charged particle. And r, the radius of the circular path described by the charged particle, okay, due to this magnetic field, due to the magnetic field, right? The magnetic force acts as a centripetal force. So magnetic force is equal to centripetal force. Magnetic force is QVB because it is maximum value, right? And centripetal force is given by the formula mv square divided by r, right? Here v get cancelled. Therefore r equal to, here mv, if QB is taking this side, okay, it goes to denominator, so Q into B. So this equation gives the radius of the circular path described by the charged particle when it is moves perpendicular to the magnetic field. Okay, the charged particle moves perpendicular to the magnetic field. It experiences maximum magnetic force which acts as a centripetal force, so that the charged particle moves along the circular path. The radius of the circular path can be calculated by using the formula R equal to mv divided by qb. M mass of the charged particle, v velocity of the charged particle, q charge magnitude, and b magnetic field. Magnetic field. If you know these four values, we can calculate what is the radius of the circular path described by the charged particle. Right. We know that velocity is nothing but displacement divided by time. Velocity is equal to displacement divided by time. Suppose let capital T be the time taken by the charged particle to complete one circle. Capital T be the time taken by the charged particle to complete one circle. Complete one circle, right? So during this time, the total distance or displacement of the charged particle or total distance covered by the charged particle is equal to the circumference of the circle. Circumference of the circle. Capital T, the time taken by the charged particle to complete one circle. During this time, the total distance traveled by the charged particle is equal to the circumference of the circle. Okay, so S is equal to 2 pi r. 2 pi r is the circumference of the circle. And time t is equal to capital T. If time t is equal to capital T, then the distance covered by the charged particle is equal to the circumference of the circle. Substitute S equal to 2 pi r and small t equal to capital T here, then V is equal to 2 pi r divided by capital T, or capital T is equal to 2 pi r divided by V. 2 pi r divided by V. Right. So what is capital T? The time taken by the charged particle to describe one complete circle. or radius of the circular path, and the velocity of the charged particle, right? And radius of the circular path is given by the formula R equal to mv divided by qb. Substitute R formula here. Then the time period t is equal to 2 pi instead of R mv divided by qb divided by v. V cancel. Right. Then t is equal to 2 pi m divided by qb. This equation is called cyclotron period. This equation is called the cyclotron period. So cyclotron period is given by T is equal to 2 pi m divided by bq. 2 pi m divided by bq. The cyclotron period depends on the mass of the charged particle, the magnitude of charged particle, okay, and magnetic field. Right. We know that a reciprocal of time period is nothing but frequency. Okay, frequency is nothing but the reciprocal of a time period. So therefore frequency F is equal to 1 divided by T value 2 pi m divided by QB. QB goes to numerator. So F is equal to QB divided by 2 pi m. So in this case, frequency means the number of complete revolutions described by the charged particle for unit time. Okay, the number of revolutions completed by the charged particle in unit time is known as frequency. That frequency is given by F is equal to QB divided by 2 pi m, because the frequency is the reciprocal of a time period. So this time period is called the cyclotron period, and this frequency is called cyclotron frequency. Right? You know the relation between angular frequency and linear frequency. The relation between angular frequency and linear frequency is omega is equal to the relation between angular frequency and linear frequency is omega is equal to 2 pi f. The relation between angular frequency and linear frequency is omega is equal to 2 pi f. Right. So substitute f, therefore f is equal to omega divided by 2 pi. F is equal to omega divided by 2 pi, or substitute f is equal to qb divided by 2 pi m here. Then omega is equal to 2 pi instead of f, qb divided by 2 pi m. 2 pi cancel. Therefore omega is equal to qb divided by m. This equation is also called cyclotron frequency. Right? But omega is angular frequency of the charged particle, and f linear frequency, or simply the frequency of the charged particle. But both the equations are called cyclotron frequency. Cyclotron frequency is f equal to qb divided by 2 pi m, or otherwise omega is equal to qb divided by m. Cyclotron period is given by t is equal to 2 pi m divided by qb. If any charged particle moves perpendicular to the magnetic field, it experiences a maximum magnetic force which acts as a centripetal force, so that the charged particle moves along the circular path. The radius of the circular path described by the charged particle is given by R equal to mv divided by qb. The time taken by the charged particle to complete one revolution is given by t is equal to 2 pi m divided by qb. The number of revolution made by the charged particle for unit time is given by f is equal to qb divided by 2 pi m, and the angular frequency of the charged particle is given by omega is equal to qb divided by m. The two equations are called the cyclotron frequency, and the time period is called cyclotron period. Right. Thank you, student. Today enough. We will see in the next class.